Today's video is about the concept of molar mass. When we look at molar mass, it's defined as the mass measured in grams of 1 mole of any substance. So if we're talking about something like a pure element, what we can do is use the periodic table in order to find out what is the mole mass of any element. Here we go. If you take a look at the key in the middle of your periodic table, we'll see that the mass that we've been using to represent the atomic mass all these years is actually the atomic molar mass. It says here it's grams per mole. So the masses that we have here are the grams per 1 mole. Now they've functioned as the atomic mass because we know that Avogadro's constant allows us to convert back and forth between the atomic mass. So for example, if we were looking at carbon is 12.01 atomic mass units, and that's due to its atomic structure, where it has 6 protons and 6 neutrons and 6 electrons. Oops, the plus there. And that's going to give us our atomic mass, and the 0.01 has to do with the varying mass of the isotopes that are present. Some isotopes of carbon have more neutrons in them, giving a slightly heavier mass. But on average, a carbon atom will have 6 protons, 6 neutrons, and 6 electrons for 12.01 atomic mass units. Now, if instead of one atom, we have 6.02 times 10 to the 23 atoms, that's 1 mole of atoms, what we find is that the mass is 12.01 grams. So that's why on the periodic table, the masses are represented as grams per mole. It's grams per 1 mole of those atoms. So that's what we can do for molar mass. Now, we use the periodic table because what we find is when we look at different substances, 1 mole of different substances will occupy different amounts of space. And that has to do with the structure of the atom. So whereas a carbon atom has 6 protons, 6 neutrons, and 6 electrons, something like a copper atom is going to be a larger atom. If we look at copper, it's got an atomic number of 29. So we have 29 protons, 29 electrons. And that is going to mean that every atom of copper takes up more physical space. So if we have 6.02 times 10 to the 23 atoms of copper, or 1 mole, that's going to take up more physical space than 1 mole of carbon atoms. And that means that 1 mole of copper is going to have a larger mass than 1 mole of carbon atoms. So because of the fact that the different atoms are different sizes and actually have different amounts of mass in them, the molar mass of every element is going to be different. And you can actually use the molar mass as a way to identify which element you're looking at, because every atom is constructed differently, every element is going to have a different mass. Now, you'll see in the picture here that we have some compounds listed as well. We can find the molar mass of compounds. The way that we do that is we take a look at the chemical formula and we simply add them up. So if we were taking a look at something like sodium chloride, the chemical formula for sodium chloride, NaCl, this tells us that 1 formula unit has 1 atom of sodium and 1 atom of chlorine. So if we were just looking at the mass of 1 formula unit, and we use formula unit because it's an ionically bonded substance, the mass of this is going to be equal to the mass of 1 sodium. And again, we go to our periodic table. Sodium is 22.99. And then we have to add in the mass of chlorine, which is 35.45. And when we add that together, we get 58.44 grams, and the unit is grams per mole. So 1 mole, sorry, no, it's not. We're doing formula units. So the unit of mass for just one particle of sodium chloride is 58.44 atomic mass units. I got ahead of myself. Atomic mass units because we're working with simply one particle, one atom of sodium, one atom of chlorine. Now, if we took this and we multiplied it by 6.02 times 10 to the 23, we now had 1 mole of sodium chloride. What we find is that the atomic mass unit mass translates into molar mass if we convert that unit to grams. So 1 mole of sodium chloride, I'm off the page, 1 mole of sodium chloride will have a mass of 58.44 grams. So we take the formula mass, or if we were talking about a covalent compound, we'd call it the molecular mass, and we simply add together the masses of the particles present, change the units to gram, and we'll get the molar mass. So like I said, if we were working with something that was covalently bonded instead of ionically bonded, so let's look at something like, we'll use sugar, C12H22O11, so a rather big compound. The way that we would find the molar mass of this, we would take the mass of a carbon atom and we would multiply it by 12. We would take the mass of a hydrogen atom, multiply it by 22 because there's 22 of them. Take the mass of an oxygen atom, multiply it by 11 because there's 11 of those. And I'm getting those masses from the periodic table. So in total, 144, if we're talking about a mole, it would be 144.12 grams, comes from the carbon atoms. In a mole of this compound, we get 22.22 grams from the hydrogen atoms. And the oxygen gives us 176 grams. We add all those up, and we find that we have a molar mass of 342.34 grams per mole, grams for 1 mole of that substance. Now, what would that look like? Here I've got a picture of 1 mole of several different substances on a balance. So this is our sugar here that we're measuring, so we can see 342 grams for that 1 mole, and you can see how much physical space the mole takes up. Here we have the element sulfur at 32 grams, so 32.06 on the periodic table because we're going to 2 decimal places there. And the mole of sulfur takes up considerably less space because this is just a single atom, whereas this is a mole of these particles bonded together. So 6.02 times 10 to the 23 of a very, very large covalently bonded particle. And that's why we get different sizes. So for your mole practice, you have page 10, where we have the chemical formulas of different compounds. You'll have to follow this system of adding up the masses of the number of each of the different particles. It gets a little bit more complicated at the end, where you'll have to figure out the chemical formula first and give that a try. And then we can move on, after you've done some practice with that, to doing some conversions with molar mass. So if we take a look on the next page, on page 11, after you've done some practice of adding up molar masses, we need to figure out how to convert between the number of grams and the number of moles. So we can look back here and say, okay, I've got a certain mass of potassium permanganate. Well, I want to know if I just took my container of potassium permanganate, poured some into the beaker, and found the mass. How could I go from the mass to how many moles are within that beaker? So the way that we can do that is using conversions, just like we did with the particles. We're going to follow the same system where we look at what are we given in the question, what are we being asked to find, and what is the ratio or the conversion factor that's going to take us between those 2 units of measure. So right here at the top it says to convert between mass and moles, we use the molar mass of the substance. Now, when we were doing particle conversions between the number of moles and particles present, or vice versa, it was always the same number. 1 mole equals 6.02 times 10 to the 23. With mass, because of the fact that every element has different sized or different massed particles, it isn't one consistent number for every single conversion. The number is constant for every element or every compound that you're working with, but it will differ between them, and we have to figure them out each time if they're not given to us using the periodic table. So if we continue reading, for elements, it's found directly from the periodic table, and for compounds, it must be calculated. So let's work through example problems 1 and 2. We want to know how much mass does 0.650 moles of aluminum have? So following the system that we've set up through our other practice, we're going to start by identifying the given value, which is 0.650 moles of aluminum. I'm going to need some conversion factor that allows me to convert that mole value to a mass value. And this is the reason why. Moles will become important in terms of why do we use moles to measure when we get into our next unit called stoichiometry. When using that unit of measure, it allows us to make connections within balanced equations and make predictions about the number of reactants needed and the number of products needed. For now, we need to know how to just convert things to moles before we start using them. Unfortunately, I don't have a device, or no chemist has a device, that directly measures out moles. We can measure out mass, we can measure out volume, which will be the next video, but we don't have a way to just directly measure the moles of something, and that's because when it comes to different elements and compounds, that's going to be a different amount. So we have to do conversions to get from mole values to mass, so you can actually put it on a balance and say, well, here it is in a beaker, that's how much I'm going to need. We're working with aluminum, which is an element, so we go straight to the periodic table. We see that it has a molar mass of 26.98 grams per mole. So we follow our system of starting with our given value, and then we're going to multiply by that conversion factor. Now, because I'm starting with moles and I want to get to grams, if I've got moles as my given, I'm going to be dividing by moles and multiplying by mass. And what I find when I put that into my calculator is that this gives me 17.537 grams. Now I can't leave my answer like that. I need to round it for significant figures. So I go back to my given value here. This is my measured value. That 0 doesn't count as significant. So I see that I've got 3 significant figures here. So I'm going to need to round my answer to represent that. So I can keep 1, 2, 3 digits, and then I have to round it off. Because this is a 3, that stays as a 5. So this ends up being a final answer of 17.5 grams of aluminum is what would give me 1 mole, or 6.02 times 10 to the 23 atoms of aluminum. Now let's take a look at an example in reverse. How many moles are present in 50.0 grams of sodium chloride? So now I'm being given the mass, and I want to know how many moles that is. So again, follow the pattern. I start with my given. I have 50.0 grams of sodium chloride, and this is where knowing how to write chemical formulas is important, because I'm going to need to use that chemical formula to calculate the formula molar mass. My conversion factor, which I'll calculate, and my wanted is the number of moles of sodium chloride. So in order to find out the conversion factor, I need to know the mass of 1 sodium plus 1 chlorine. 1 mole of sodium chloride will be equal to, and I can do the work on a piece of scrap paper or off to the side. So sodium, we did this example in the last set of examples actually, 22.99. I have just one of them, and then chlorine, I'm going to add that to 35.45. Again, just one of them. And that's going to give me, well, like I said, we actually already did that example back here, 58.44 grams. So here my conversion factor will be 1 mole of sodium chloride is equal to 58.44 grams of sodium chloride. Set up my conversion the same way. Instead of using the multiply by the fraction, I'm going to use the chemist conversion table. So we set up a table like this. The given value goes here. So that's going to be 50.0 grams. Because I'm starting with grams, I want to divide by that to cancel out the unit of grams. So 58.44 grams goes at the bottom. 1 mole goes at the top. So when I divide, these are going to cancel. The way that the table works is the same way as multiplying by that fraction. We multiply the numbers on top and then divide by the numbers at the bottom. Now, because multiplying by 1 or dividing by 1 doesn't change your answer, essentially when you do your calculator work, you can skip this, and we just take our 50 grams and we divide it by 58.44 grams per mole, and we find that we get an answer of 0.855578371, and we're going to need to round that. So in terms of our final answer, that would be our rough answer. Now we go back to our given value, we can see that at 50.0, that's 3 significant figures. A 0 after a decimal place is significant. Otherwise, we wouldn't have it there, right? 50 on its own is the same as 50.0. 0.0 tells us that there was a level of precision in our measurement which allowed us to know that place value. So 1, 2, 3 significant figures. When I look at my answer here, this 0 doesn't count as significant. It's a placeholder telling us there's nothing there and we have to move over to the decimal places. So I can keep 3 of these digits, 1, 2, 3. I have to round it there. The 5 tells me to round up. So my final answer is 0.856 moles of sodium chloride. And that's all there is to mass and mole conversions. So we've got 2 sets of practice problems at the bottom of the page, one going from grams to moles and the other going from moles to grams. Give those a try. The answer keys will be posted soon.